Hello everyone, my name is Jaina Reddy. I'm a CSC data student at IRE Hyderabad. In this video, I'm going to explain about the graphic signal processing for machine learning, a review and new perspectives. So, the effective representation, processing, analysis, and visualization of large-scale structured data, especially those related to complex domains such as networks and graphs, are one of the key questions in modern machine learning. Graph signal processing (GSP), a vibrant branch of signal processing models and algorithms that aims at handling data supported on graphs, opens new paths of research to address this challenge. In this article, we review a few important contributions made by GSP concepts and tools such as graph filters and transforms to the development of novel machine learning algorithms. In particular, our discussion focuses on the following three aspects: exploiting data, structure and relational priors, improving data and computational efficiency, and enhancing model interpretability. Furthermore, we provide new perspectives on the future development of GSP techniques that may serve as a bridge between applied mathematics and signal processing on one side and machine learning, and network science on the other. Cross-fertilization across these different disciplines may help unlock the numerous challenges of complex data analysis in the modern age. Introduction. We live in a connected society. Data collected from large-scale interactive systems, such as biological, social, and financial networks, become largely available in parallel. The past few decades have seen a significant amount of interest in the machine learning community for network data process and analysis. Networks have an intrinsic structure that conveys very specific properties to data. Example, interdependencies between data entities in the form of pairwise relationships. These properties are traditionally captured by mathematical representations such as graphs. The push for more efficiency representation of graphs collected in new structured observation domains has led to recent development of GSP 123. GSP is a fast-growing field at the intersection of applied mathematics and signal processing that has seen a significant amount of research effort in the signal processing community at large. In these settings, data are modeled as signals defined on the node set of a weighted graph, which provide a natural representation that incorporates both the data node attribute and the underlying structure each attribute. By extending classical signal processing concepts such as sampling, convolution, and frequency domain filter to signals on graphs, GSP provides new ways of leveraging the intrinsic structure and the geometry of the data in the analysis. This provides a generic framework and numerous appealing tools to address some of the new challenges encountered by current machine learning models and algorithms that handle network data. GSP for expand data structure. GSP typically permits one to model, analyze, and process data supported on graphs. For ease of discussion, consider a weighted and undirected graph GV is equal to comma E with the node set V of cardinality and its set E. A a graph signal is defined as a function x equals to x such that V R that assigns a scalar value to each node. The main research effort in GSP is therefore concerned with the generalization of classical and signal processing concepts and tools to graph signals. One key development is that the a set of eight eigenvectors of the graph Laplacian matrix or a graph shift operator, a generic matrix representation of graphs, provides the notion of frequency on graphs and helps define the so-called graph Fourier transform, GFT. For example, consider the combinatorial graph Laplacian LD equals to minus W, where W is the weighted adjacency matrix of the graph and D is the degree matrix. The graph Laplacian L admits the eigen composition L T equals to UKU, where U is the eigenvector matrix that contains the eigenvectors as columns and K is the eigenvalue matrix tagged MM1 to FMN that contains the associated eigenvalues conventionally sorted in the increasing order along the diagram. Due to the analogy between the continuous Laplace operator and the graph Laplacian L, the operation XX TGHUU and equals to can be thought of as GFT of the graph signal X with the ith entry of XTU being the Fourier coefficient that corresponds to a discrete frequency Fibonacci depends on an illustrative example of a typical graph-based machine learning task and the corresponding parameters. The input of the algorithm consists of a typical protein interaction network captured by graph and a signal on the graph, color code, that is expression level of individual genes at any given time. The output can be classical machine learning tasks, such as clustering of blood proteins or prediction of gene expression over time. So G is the protein interaction graph, and X is the expression level of individual genes. So from there, graph-based machine learning is implemented. The challenges are explaining structure, computational and data efficiency, and interpretability. The tasks are protein grouping, prediction of gene expressing types, that is clustering and regression. Regression for multiple response variables. Regression is one of the basic forms of supervised learning where, in its simplest setting, we are interested in learning a mapping from a set of inputs or features to a real value output or response. Of particular interest is the generalized problem of multivariate regression, where we can learn such a problem, such a mapping for multiple response variables. Existing approaches in the literature usually rely on some type of modeling of the interdependencies between the response variables. For example, For example, so, for example, in a parametric model, such interdependencies are implicitly captured by the provisions of a multivariate and autoregressive process. In a non-parametric model, that may be explicitly modeled by the kernel function of the multi-output Gaussian process. GP. In particular, in the case of separable kernels for multi-output GPR, a positive semi-definite UST matrix is incorporated into the kernel function when the interactions among the response variables. Graph-based classification. Another basic form of supervised learning is classification, which is similar to regression but with a categorical response variable. Recent advances in deep learning in the particular and convolutional neural networks (CNNs) have led to significant improvements in tasks such as image classification. However, classical CNNs cannot be directly applied to classify signals that are supported on the graph structure due to lack of notion and shift and convolution in the irregular graph domain. GSP provides a convenient tool to address such a challenge. More specifically, by providing a notion of frequency and a GFT. Convolution may be implicitly defined via the graph spectral domain. Consider a graph signal X and a convolutional graph kernel GT of it, which is defined directly in the graph spectral domain as a function applied to the Laplacian eigenvalues. Figure 2. The graph convolution via polynomial spectral graph filters proposed in the subnet architecture. An input graph signal is passed through three graph filters separately to produce the output of the first graph convolutional level before nonlinear activation and graph filling of the subnet. Input graph signal, graph filter, and graph convolution output. So we can see the diagrams. The input graph signal, graph filter, and the graph convolution output. GSP for improving efficiency and robustness. Although GSP is a framework originally developed for incorporating the graph structure into data analysis, recently many classical machine learning algorithms have also benefited from exporting typical GSP tools. Significant improvement in terms of robustness with respect to sparse and noisy training data. For adversarial examples has been shown in tasks such as semi-supervised learning, few-shot learning, zero-shot learning, and multitask learning. Furthermore, large-scale data analysis and statistical learning can benefit from typical GSP operations, such as sampling and filtering, to reduce the computational complexity and time of graph-based learning. We discuss some of these aspects in the following sections. Improvement on data efficiency and robustness. Graph regularization has been introduced in many learning architectures, including guidelines to improve the performance of supervised and semi-supervised learning tasks. In semi-supervised settings, the loss term has been augmented by graph-based parameterization term that biases the network toward learning similar representations for neighboring nodes on a graph that contains and has nodes both level and unlabeled data. In supervised learning problems, the regularization technique that encourages smoothness of the label signal on a similarity graph structure constructed from the data has been shown to improve the Robustness of a deep learning architecture is by maximizing the distance between outputs of our different classes. Robustness in topological models. In addition to robustness in terms of data samples, another master consideration is the stability and robustness of back-based models, that is topological models. This usually means perturbation in the graph topology, which may be due to noise observed in real-world graphs or inaccuracy in the inference of the graph topology. Is one of the is one is not If one is not readily available. Stability and robustness against such perturbation is the key to generalization capability of graph-based machine learning models. Figure 3 illustrates an illustrative example of single task network and a multitask network. Nodes represent individual tasks, each of which is to be info a parameter vector W O, which optimizes a with differentiable cost function. In a single task network, all tasks optimize for the same parameter vector W O, while in a multitask network, they optimize for distinct though related parameter vectors W. Thank you.